Welcome to the lecture series on CFD, Part 2. This is lecture 32A on turbulence modeling for Reynolds-averaged Navier-Stokes equations. This lecture starts with an introduction to turbulence modeling approach. We present the concepts of time and ensemble averaging, mean values, and fluctuations of variables. Next, the Reynolds-averaged Navier-Stokes equations, Reynolds stresses, and turbulent scalar fluxes are presented. We then introduce the most widely used concept of turbulence modeling, the eddy-viscosity approach. To compute the eddy or turbulent viscosity, we need to determine the velocity and the length scale of turbulence. Many turbulence models require the computation of turbulent kinetic energy, from which the velocity scale is determined. We present the exact equation for it and the models for terms which include additional unknowns. Turbulence models from the K-epsilon family require the solution of an additional equation for the dissipation rate of turbulent kinetic energy, which is used to determine the length scale. Another family of models solves the equation for another variable, omega, to compute the length scale. Both equations and their modeling are presented. Finally, the Reynolds-stress class of models is briefly described. These models solve equations for Reynolds stresses and turbulent scalar fluxes. This leads to a significantly higher computing effort than in the case of two-equation models, which is magnified by slower convergence due to the stiffness of the equation system. Engineers are most often only interested in integral quantities from turbulent flows, like forces on bodies, mixing of fluids, heat transfer rates, etc. If all information about turbulent flow was available, the integral quantities could be obtained by averaging. Two kinds of averaging are used in turbulence research: averaging over time, if the flow is statistically steady, or averaging over an ensemble of realizations in which all controllable factors are kept the same, for example, unsteady flow in a cylinder driven by piston motion. If the governing equations are averaged in this way, we obtain the Reynolds-averaged Navier-Stokes equations, or RANS equations. The problem is that the resulting equations are no longer closed. They contain more unknowns than there are equations. Therefore, approximations and additional equations are needed to solve the RANS equations for mean variables. Due to the complexity of turbulence, it is unlikely that a single model will ever work well for all applications. Therefore, turbulence models should be regarded as engineering approximations rather than scientific laws. Statistical analysis of turbulent flow introduces mean quantities and their fluctuations. At any point in time, defined by the position vector xi, and any instant of time, the instantaneous variable phi can be expressed as the sum of the mean value and the fluctuation around it, as shown by this expression. In the case of time averaging, the mean value of phi at a given location xi is defined as the integral over time divided by the integration interval t, when the length of the interval tends to infinity. The mean value varies in space, but not in time. In the case of ensemble averaging, the mean value of phi at a given location xi and time t is defined as the sum of variable values recorded at the same location in space and the same time relative to the reference point over n realizations divided by n when n tends to infinity. The mean value in general varies in both space and time. This plot shows schematically the variation in time of instantaneous velocity component u at a fixed point in space, its mean value, and the fluctuation at an instant of time. By definition, the time average of the fluctuation is zero. This plot shows schematically the variation of u over time at a fixed point in space in one realization of the flow, for example, during the intake stroke in an internal combustion engine. The ensemble average mean value and the fluctuation around it are also indicated. By definition, the ensemble average of the fluctuation is zero. Averaging is applied not only to individual variables, but also to the governing equations. By definition, every linear term containing fluctuations drops out of the equation. Terms containing products of variables, like the quadratic nonlinear convection term, leaves after averaging the product of mean values and the covariance, that is, the average of the product of two fluctuations. The products of mean value of one variable and the fluctuation of the other variable drop out after averaging. In this case, that applies to the products of mean u times phi prime and the product of mean phi and u prime. For an incompressible flow, the Reynolds-averaged Navier-Stokes equations and the generic scalar transport equation after averaging are given by these expressions. The continuity equation looks like its instantaneous form because it does not contain nonlinear terms and fluctuations drop out through averaging. As indicated in the preceding slide, the nonlinear convection terms lead to an additional term in the average momentum equations, which is indicated by red frame. The same is true for the scalar transport equations. The pressure term and the term containing viscous stresses remain unchanged after averaging because they are linear. Each of the three momentum equations contains three terms involving average products of fluctuations. These terms form the Reynolds-stress tensor, which, due to its symmetry, contains 6 unknowns. All terms involving products of fluctuations are moved to the right-hand side of the equations. The Reynolds-stress tensor is thus defined as follows. Note that in literature this tensor is often written without density, in which case the components do not have the dimension of a stress, which is Newton per square meter. The conservation equation for a scalar quantity phi contains three terms involving average products of velocity fluctuations and scalar fluctuations. These three terms form the turbulent scalar flux vector, given by this expression. It brings three new unknowns into each scalar equation. In the Reynolds-averaged Navier-Stokes equations, we have four averaged equations, one for mass and three for momentum conservation. These four equations contain four mean variables and 6 average products of fluctuations. Thus, the equations are not closed and cannot be solved without approximations or extensions. This is called the closure problem in turbulence modeling. The simplest approach is to express the additional variables from mean values and/or engineering correlations, which leads to the so-called zero equation turbulence models. They are hardly used today and will not be further considered. In laminar flows, energy dissipation and transport of mass, momentum, and scalars in cross-flow direction is performed by diffusion. This is accounted for by viscous stresses and diffusion fluxes, which depend on velocity and scalar gradients and fluid properties, viscosity and diffusivity. These properties are, in most cases, determined experimentally. They are usually a function of temperature and possibly pressure or concentration. Turbulence also enhances transport in cross-flow direction. As shown in slide 7, the origin of this transport lies in convection terms, but it is compelling to model it in the same way as diffusion is accounted for in laminar flows. This leads to the so-called eddy-viscosity and eddy-diffusivity approach. With this approach, the Reynolds-stress tensor is approximated as follows. This part looks like the mean viscous stress tensor defined in slide 7, with fluid viscosity replaced by a yet unknown turbulent viscosity μt. The last term is required to guarantee that the sum of diagonal elements gives 2 rho k, where k is the turbulent kinetic energy. See next slide. The sum of diagonal elements of this part is equal to 0 due to the continuity constraint. Analogously, the turbulent scalar flux vector is approximated using the gradient hypothesis as in the Fourier law, only that the fluid diffusivity is replaced by a turbulent diffusivity, gamma t. Even this simple approach introduces, in addition to turbulent viscosity, one more unknown, the turbulent kinetic energy, defined as follows. The trace of the Reynolds-stress tensor is thus equal to 2 rho k, which required adding the second term to the model of Reynolds stresses. Eddy-viscosity and diffusivity are obviously not fluid properties. They vary in space, often by 3 to 4 orders of magnitude, and depend on the solution of Reynolds-averaged Navier-Stokes equations. Dimensional analysis requires that viscosity be proportional to a product of velocity scale Q and a length scale L. This is why turbulent viscosity is defined as the product of density, velocity scale, and length scale, and an additional dimensional parameter C mu, which is in most models assumed to be a constant. The question is now how to determine the velocity scale Q and the length scale L. Turbulent kinetic energy has a dimension of squared velocity, so an obvious choice for the velocity scale is Q equals square root of 2k. The length scale can be prescribed as a function of wall distance for the near wall region in boundary layer flows. Based on experimental observation, L varies linearly with distance from wall in such flows. However, for complex flows and away from wall, no good estimate is available. This suggests that the required parameters must be obtained by solving additional equations. An equation for turbulent kinetic energy is easily derived from Navier-Stokes equations, but it contains triple correlations, that is, average products of free fluctuations, and thus introduces even more new unknowns. The equation is shown in the next slide. The complete equation for turbulent kinetic energy is given by this expression. It is obtained by multiplying the instantaneous momentum equations by corresponding velocity fluctuations, summing the equations and taking the average of the resulting equation. The first three terms framed in blue do not require modeling. They can be computed in their exact form. The remaining three terms framed in red contain average products of 2 or 3 fluctuations of variables and thus require approximations involving only the mean variables and empirical parameters. None of the terms can in general be neglected. The first term to be modeled represents turbulent diffusion of kinetic energy. It is actually the transport of velocity fluctuations by fluctuations themselves, but is almost always modeled using a gradient diffusion assumption. This means that the gradient of k is multiplied by the diffusion coefficient, which is defined as the ratio of turbulent viscosity and turbulent Prandtl number, by analogy to the definition of diffusivity coefficient in laminar flows. The turbulent Prandtl number is an empirical parameter taken to be around unity, independent of the flowing fluid. The next term to be modeled represents the rate of production of turbulent kinetic energy by the mean flow, that is, a transfer of kinetic energy from mean flow to turbulence. The Eddy-viscosity hypothesis for the Reynolds stresses leads to the following expression for the model of the rate of production of turbulent kinetic energy. The last term to be modeled is a product of density and the dissipation rate, epsilon. It is the rate at which turbulence energy is irreversibly converted into internal energy, that is, heat. There are also more complex models in which eddy viscosity is a tensor. By solving the transport equation for turbulent kinetic energy, we can define the velocity scale. Another equation is needed to determine the length scale, and the choice is not so obvious. Experimental observations lead to the conclusion that in the so-called equilibrium turbulent flows, the following relation holds. In equilibrium turbulent flows, the rates of production and destruction of turbulence are in near balance. This is the case in some fully developed flows, as will be shown in the next slide. Thus, if one solves an equation for epsilon in addition to one for k, one can compute both the velocity scale and the length scale, leading to the following expression for eddy viscosity as a product of a dimensionless parameter C mu, density, turbulent kinetic energy squared, and divided by epsilon. This closes the system of equations. Turbulent viscosity is expressed via two new unknowns, which are obtained by solving two additional transport equations. This plot shows profiles of normalized turbulence production and dissipation rates in a boundary layer of a flat plate, in a plane channel, and in a pipe. The plot is created using data obtained from DNS of such turbulent flows at moderate Reynolds numbers. The rate of production of turbulent kinetic energy is shown by full lines and its dissipation by dashed lines. Note that the two rates are nearly equal in the zone where the velocity profile varies logarithmically near wall for all three flow types. Outside the log-low region, the rates differ to some extent, but the differences are large in the viscous sublayer and in the buffer layer. More information about these zones in a velocity profile will be given in lecture 32b. An exact equation for epsilon can be derived from the Navier-Stokes equations because the dissipation rate is defined as the product of kinematic viscosity and gradients of velocity fluctuations. However, only the convection and rate of change terms, framed in blue, are exact. All other terms on the right-hand side of the equation, framed in red, need to be modeled. The whole equation should therefore be considered a model. This completes the so-called K-epsilon turbulence model. The standard values of the various constants determined by fitting the results to experimental data for many flows at high Reynolds numbers are listed here. With Eddy-viscosity models, momentum equations for averaged velocities look the same as in the case of laminar flow. One only needs to replace the fluid viscosity with an effective viscosity defined as the sum of molecular viscosity and turbulent viscosity. One also must account for the spatial variation of eddy viscosity by several orders of magnitude and its nonlinearity. Because both K and epsilon exhibit strong variation near walls, in recirculation zones, and in body wakes, turbulent viscosity varies also rapidly there. Therefore, under relaxation of changes in effective viscosity may be required. The outer iteration loop of the simple-like algorithms is easily extended to accommodate the computation of K and epsilon. This will be shown on slide 20. Coupling equations that compute turbulence quantities with mass, momentum, and energy equations is very difficult. Momentum equations depend strongly on turbulent viscosity, which is proportional to the ratio of K squared over epsilon, and these quantities are strongly influenced by velocity gradients. Thus, even when a coupled solver is used to compute velocities, pressure, and temperature, equations for K and epsilon are solved sequentially as in the simple method. Both K and epsilon are by definition non-negative quantities. Therefore, one must ensure that they cannot become negative in the numerical solution method, not even in the intermediate stage of iterations. Both K and epsilon have pronounced peaks near wall, which cannot be resolved by a coarse grid. Therefore, the grid should be finer near the wall than elsewhere. Higher-order convection schemes can produce over- and undershoots near peaks in profiles of K and epsilon. This could lead to negative values of K and epsilon in near-wall regions, which is why limiters or local blending with lower-order dissipative schemes is required to preserve positive values. It is important to use a second-order or higher-order convection schemes for velocities to obtain accurate velocity profiles and gradients. For K and epsilon, one can afford lower-order discretization near walls because source terms dominate the equations there. These source terms are dependent on velocity gradients, and if velocity profiles are accurate, K and epsilon will come out correct. There are many variants of the so-called standard K-epsilon turbulence model. Low-ray versions with modifications near wall to account for low velocity and wall damping effects, realizable and nonlinear versions, and many others. Several modifications were proposed to compensate for some weaknesses in particular situations, for example, a correction to prevent overproduction of turbulent kinetic energy stagnation points or lines. The velocity gradient is high there, but turbulence level is low, unlike in other parts of the flow with high velocity gradients. And a correction to account for the curvature of streamlines, as well as many others. The sequential solver of simple type solves equations in turn. In SimCenter and Plus software, this solver is called segregated. First, momentum equations are solved. Then, the continuity equation, that is pressure correction equation, then equations for scalars, like energy, turbulence model equation, etc., as shown in this diagram. We distinguish between inner iterations within linear equation solver, where equations are solved with the coefficient matrix as source vector frozen, and outer iterations in which the coefficient matrix and the source terms are updated. Note that for legacy reasons, outer iterations are SimSet Stasis M plus called inner iterations, and iterations within linear equation solver are just called iterations. When conjugate heat transfer is involved, the outer iteration loop spans all fluid and solid regions. Outer iterations are needed because in general each variable depends on all other variables. Ra's equations are highly nonlinear coupled equations and require under relaxation or time marching to promote convergence of iterations. See slides 5 to 7 of lecture 11 and section 543 in the book for details about under relaxation. Another family of popular two-equation turbulence models based on Eddy-viscosity approach are the K-omega models. In these models, the velocity scale is also determined from the turbulent kinetic energy K, but another variable, omega, is solved to determine the length scale. The model equations are given by these two expressions. In addition to the rate of change in convection terms on the left-hand side, these equations contain on the right-hand side a production term, a dissipation term, and a diffusion term. The eddy viscosity and the constants are given here. Menta in 1994 has proposed a version of this model which actually blends the K-omega model in the near wall zone and the K-epsilon model away from walls. This is the most widely used version from this family of models, called SST version of the K-omega model. SST stands for shear stress transport. In 2 dimensions, eddy viscosity can be tuned to give perfect results. However, in 3 dimensions, the relation between Reynolds-stress and strain rate may be so complicated that eddy viscosity will have to be a tensor for the linear constitutive relation to be valid. Eddy viscosity models have many deficiencies which are usually mended by various corrections. Computer cores try to be intelligent and switch these on and off where needed. A potentially better model can be obtained by solving equations for Reynolds stresses themselves and not rely on eddy viscosity hypothesis. Models of this kind are as old as the eddy viscosity ones, but have not been used so widely because they are more difficult to implement in computer codes and lead to equations that are more difficult to solve. Let us now see how Reynolds stress models work. The transport equations for Reynolds stresses, given by this expression, can be obtained by manipulating the Navier-Stokes equations. The process involves multiplying momentum equations by velocity fluctuations and averaging. We skip the derivation and show only the final result, 6 equations for the 6 tensor components. The terms on the left-hand side and the first 2 on the right-hand side, framed in blue, are exact and require no modeling. The remaining terms, framed in red, cannot be computed without approximation and must be modeled. Let's see what these terms look like. The first term in this group is the dissipation tensor, given by this expression. The following term is called pressure strain term. It redistributes the turbulence energy between components, but does not change the total kinetic energy. Its exact definition is given by this expression. The first term in brackets in the last part of the right-hand side from previous slide, given here, is exact and requires no modeling. It is usually also very small and can often be neglected in flows at high Reynolds numbers. The last term on the right-hand side is often called turbulent diffusion. It is defined by the following expression. The dissipation, pressure strain, and turbulent diffusion terms involve new unknowns, including triple correlations, that is, average of products of free fluctuations. Therefore, these terms must be modeled, that is, expressed via quantities for which equations are solved and empirical parameters. The simplest and most commonly used model for dissipation is to treat it as isotropic. Under this assumption, the dissipation tensor can be expressed via the dissipation rate from the K-epsilon model as follows. This means that an equation for the dissipation rate epsilon must be solved along with 6 equations for the Reynolds stresses. More sophisticated models for the dissipation tensor were proposed but are seldom used. Thus, the weakest element in the modeling chain of Reynolds stress models is the equation for epsilon. The simplest model for the pressure strain term is to assume that it tends to make the turbulence more isotropic, but the results obtained with this assumption are not very good. Many more complicated nonlinear models for pressure strain term have been proposed. They will not be presented here. The turbulent diffusion part is usually modeled using the gradient diffusion approach given by this expression. All model terms are very important, but their relative magnitude varies from one flow to another. Because of that, the results obtained depend on application and are not always better than those from K-epsilon models. The equation system resulting from the Reynolds-averaged Navier-Stokes equations and Reynolds-stress model equations is very stiff if Reynolds stresses are simply inserted into momentum equations as source terms. Better convergence is obtained by implementing Reynolds stresses via deferred correction terms. Eddy-viscosity model is used implicitly, so momentum equations contain diffusion terms with turbulent viscosity. The difference between Reynolds stresses computed by solving their equations and the Eddy-viscosity model for them is a source term computed with values from previous iteration. The equations for Reynolds stresses also require care when the numerical solution method is applied on collocated grids in order to avoid decoupling problems. This is akin to the Ryan-Chow term used to correct phase velocities in the continuity equation. See slides 22 and 23 in lecture 18 for details. As already mentioned, Reynolds stress models do not always lead to better results than K-epsilon models. However, there are situations in which Reynolds stress models always perform better than Eddy-viscosity models. Here are some examples. Turbulence-induced secondary flows, flows with streamline curvature, swirling flows, transitional flows, unsteady flows, and flows in stagnation regions. This plot shows turbulence-driven secondary flow in a rectangular channel. Eddy-viscosity type models cannot predict this type of flow. Velocity vectors are projected onto a cross-section perpendicular to channel axis. Fluid is driven by turbulence into corners and moves then along walls towards symmetry plane. Similar patterns result in other non-circular flow channels. These two plots show flow around an inclined prolate spheroid, streamlines, and secondary velocity vectors in one section plane. Eddy-viscosity type models have problems with predicting flows of this type. In addition to many variants of turbulence models described in preceding slides, there are also many other models which do not fall into those categories. We mention only a few. Spalart-Almaras model. It solves one additional equation for turbulent viscosity and prescribes the length scale. It has been used with success for boundary layer flows, for example, around airfoils. Algebraic Reynolds stress models, often denoted as ARSM, and explicit ARSM. In these models, additional approximations are used to convert partial differential equations into algebraic equations for Reynolds stresses. They usually require that transport equations are solved for K and epsilon and are similar in performance to the nonlinear K-epsilon models. V2F model. It solves 4 additional equations, has some advantages over 2 equation models, but is less robust. And transition models. They solve 1 or 2 additional equations, aiming to distinguish between laminar and turbulent part of the flow. See section 10.3.5 in the book and the references therein for more information about these and other turbulence models. Here is a summary of this lecture. In many applications, engineers are only interested in the average flow features. Averaging can be applied over time or an ensemble of realizations. This is called Reynolds averaging. The Reynolds-averaged Navier-Stokes or Rav's equations are not closed. They contain more unknowns than equations because nonlinear terms leave after averaging so-called Reynolds stresses, average products of velocity fluctuations. One can derive equations for Reynolds stresses, but they contain high-order unknowns, average products of 3 or more fluctuations. Therefore, some kind of approximations must be used to solve the Run's equations. Most widely used are so-called two-equation turbulence models based on Eddy-viscosity hypothesis. To determine the turbulent viscosity, we solve an equation for turbulent kinetic energy K, which defines the velocity scale, and another equation for a quantity which allows us to determine the length scale, epsilon or omega, both related to dissipation of turbulent kinetic energy.